partnership projects, which meant that there were a lot of scientists coming to IIT Madras, and also a lot of Indian scientists being trained in Germany. You have still a very, very strong German collaboration. So we have the German Center for Sustainability. Also very interesting to see IIT Madras longer history of Indo-German relationships, specifically also Indo-German relationships in history of science.
Talking about consumer electronics, every time you use a mobile phone, it makes use of an analog mixed signal IC design, which IIT Madras has the most leading centers for. The world of tomorrow is going to be more electric driven than it is today. And that leading edge technology is being created right now in IIT Madras.
Hello and good evening to everyone. Thank you for joining us today. The Institute of Eminence scheme was launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the Select Institute of Eminence. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway at IIT Madras. As a part of these initiatives, the IRIS webinar series aims to showcase the innovative research being generated to various stakeholders like students, researchers, industrialists, and policymakers. On behalf of the Office of Global Engagement, it is my pleasure to welcome you to the 44th webinar from the IRIS webinar series. My name is Ujjwala K, and I am a part of the Office of Global Engagement. Today's webinar is from the Quantum and Science Technology Cluster. The research initiative presenting today is Quantum Information, Communication and Computing, led by Professor Anil Prabhakar. This research initiative covers a wide range from information theory to device design and characterization and the building and characterization of systems. The center is also keen to undertake technology transfer and support the training of the workforce in quantum science and technology. Our speakers of today are Professor Anil Prabhakar, Dr. Prabha Mandayam. Professor Anil Prabhakar is in the RF and Photonics group from the Electrical Engineering Department at IIT Madras. His current research is focused on photonic technologies for quantum communications and non-Boolean computing. He is also involved in several IITM incubated startups and a member of the LIGO India Scientific Management Board. Thank you for being with us today, Professor Anil. We are very excited that you could be a part of this session. Dr. Prabha Mandayam is in the Department of Physics at IIT Madras. She obtained her PhD from the Institute of Quantum Computing at Caltech. After working as a postdoctoral fellow at the Institute of Mathematical Sciences and Inspire Faculty Fellow at the Chennai Mathematical Institute, she joined IIT Madras as a faculty in 2014. Her research interests include quantum error correction and quantum cryptography. Our moderator for today, Professor David DiVincenzo, is the director of the Institute of Theoretical Nanoelectronics at the Peter Grimberg Institute in Jülich and professor at the Institute of Quantum Information at RWTH Aachen University. He is a fellow of the American Physical Society and is well known for his work on quantum information processing and Los DiVincenzo criteria for implementing quantum computers. Professor DiVincenzo, we extend you a special welcome to the event. We also have distinguished panel members from various departments at IITM, namely Physics, Electrical Engineering, Mechanical Engineering, and Department of Management Studies. So before we start, a note to the participants, please use the Q&A section to enter your questions and upload the questions that interest you so that the moderator can prioritize them later. And thank you, and over to Professor Anil Prabhakar.
Thank you, Ujjwala, for that kind introduction. I'm going to just make a quick correction. Prabha is going to be on the panel, but she's not speaking today. But she will get first dibs at introducing the panel when we start the panel discussion. Okay. Everything else you said about her was absolutely correct. All right, let me just share my screen. Okay. As Ujjwala introduced the topic today, we are talking about quantum information, communications, and computing. I'm at the Department of Electrical Engineering, and you will find more details about the Center of Excellence at the website quantum.iitm.ac.in. I do not take credit for most of what I'm talking about. I do have a large number of collaborators, and I will introduce you to them as, or introduce them to you as I go along with my presentation. The center itself has three main focus areas. We work on quantum networks, we work on quantum computing, and we work on quantum information. One of the central themes that joins these three areas is the idea of photonics, which is my own specialization. And we are looking at using the entanglement and superposition properties of photons to address problems in these focus areas. So you can look at quantum networks, or you can look at quantum communications. You can also look at more complicated versions of quantum communications like secret sharing. When you start talking of quantum computing, a lot of the applications today are in quantum computing with machine learning and optimization. We also build what are called Ising machines using photonics and cluster states. And when we talk about quantum information, we are talking in terms of simulations, algorithms, error control codes, tomography. A lot of this information about the quantum systems that we are working with is extracted using some of the ideas that quantum information scientists provide to us. As a very brief introduction, let me explain to you why people are interested in quantum computing, right? And we have here a simple idea of what is called a block Poincare sphere. And it tries to bring out the difference between a bit and a qubit. Everybody knows what bits are. They are binary, they're 0 and 1. And if you think of the 0 and 1 being the north and the south pole on this block Poincare sphere, you will find that qubits are continuous. They could lie anywhere on this sphere. And what you do understand also is that if they can lie anywhere on the sphere, they can be described in what is called a superposition state. This is shown on the right. It is a vector that is pointing at a particular location on the unit sphere. And so the amplitudes associated with the North Pole and the South Pole are normalized so that the amplitudes add up to 1. Right? So that's a very basic idea. And that's in some sense what helps us, because when we start increasing the number of qubits, what we also do is we increase the number of computational paths. So on the left is a very simple idea that if you have, let us say, 8 qubits, you have 256 computational paths. And we understand that in some sense using the ideas of interference. There's a little cartoon here that shows if you have 2 stones dropped in a pond, you see the waves, you see the ripples, and they start interfering. If you have many more stones, they interfere a lot more. And you can imagine that as the computational paths start increasing, the computational power that we have increases tremendously. So by the time you get to 64 qubits, you do have a seriously large number of computational paths. Now that of course is in theory. What happens in practice is something completely different. So on the right out here, we are looking at a quantum computer, and we see that the quantum computers are all connected in a particular geometry. So if you're looking at a Rigetti machine or you're looking at an IBM machine, they're all connected. So one is connected to 2 and 2 is connected to 3, but one is not necessarily connected to 16 unless you go through all the other qubits. And that in some sense is a limitation because these qubits can be noisy. And if they're noisy, then you don't necessarily connect 2 arbitrary qubits on a lattice. And you have to go through other qubits, and in doing so, you degrade your information. So a lot of the power today that we have in quantum computers is actually limited because of the way the qubits are connected and because the qubits are noisy. Understanding that actually gives us a lot of power because we are able to then design algorithms to implement them on this. So we are in what we call the noisy intermediate scale quantum era, right? The NISQ era. And that was an acronym coined by John Preskill, who also said that quantum error correction is what allows us to think of scaling these quantum computers. So to the left, you have 2 histograms, one of a simulation that is run on an ideal quantum computer, on an ideal quantum simulator, and the second one, which is run on a 5-qubit IBM quantum processor. And we're supposed to get 0, 1 as the answer to the simulation. And you'll notice on the actual quantum computer, you get a probability. You get 0, 1 most of the time, but you don't necessarily get it all the time. So there is a probability of you getting the wrong answer, which means that it's not the same as punching numbers in your calculator. If I say 2 into 2 is equal to 4 on my calculator on a quantum computer, I'll get 4 maybe 999 times out of 1,000. But there is still this finite probability that I don't get 4. So in some sense, quantum computing is also probabilistic, and we need to understand when we want to use a quantum computer. It is not true that quantum computers are going to solve all our problems. We have to pick and choose our problems before we implement them on quantum computers. So when do we use a quantum computer? Well, here's an example of 2 algorithms. One is called Grover's search and one is Shor's factoring. These are the famous algorithms that have started some of the research in this field. And what it says is that the blue line is when you're doing classical searches, and the red line is when you're doing searches on a quantum computer. And depending on the size of the problem, there comes a transition, an inflection where the quantum computers become more powerful than the classical computer. So obviously, if you want to do 2 into 2 is equal to 4, please don't go running it on a quantum computer. You can do that on your calculator, or if you need a calculator. Right? So what do we do with the quantum computers? We run a different kinds of problems. So here are some examples. There is optimization, there's machine learning, there are simulations. Simulations of molecules is very popular today because those follow the laws of quantum mechanics, and it's easier to solve such problems on a quantum computer. Optimization is used everywhere. It's used for vehicle routing, it's used for bin packing. There are a large number of problems that use optimization. And the graph or the picture out there says that you have some metric on the y-axis. And what you're trying to do is find the minimum of that metric, right? So it could be energy, for example, and you're trying to find the minimum energy state. There is another way of doing this on a quantum computer. There are 2 types of quantum computers. One which uses universal computing, which is what companies like IBM, Google, Honeywell use. There is the idea of quantum annealing, which is what a company like D-Wave does. And in this particular cartoon, what D-Wave is trying to say is that, look, we don't necessarily need to find a minimum energy state systematically. We can just hop around different local minima and try to get to the global minima. Both these approaches are competing today, and they're both available on the cloud. And that is where a lot of the research that we do on applications comes in. So what are we using these quantum computers for? They're mostly NP hard problems. As I mentioned, bin packing, there is route optimization, there is image classification, there's portfolio optimization, there are quantum simulations. And these translate across different areas. There's basic science, there's translation research, and there are industrial applications. One of the holy grails is cryptography, which is basically to say that if you give me a quantum computer, I will be able to crack your password. I don't think that's going to happen anytime soon, but that is one of the driving motivations for a lot of the work that is done on quantum computers. So what does this race to quantum supremacy that we keep hearing about? It's sort of the idea that at some point you will be able to get enough noisy qubits that you can run near-term applications that demonstrate the power of quantum computers. And as I mentioned, one of the areas of, one of the reasons people are interested in it is to look at what our public key infrastructure and determine whether it is secure. But when will we know that this public key infrastructure is secure or insecure? Most likely you will not know immediately if it is insecure. The people who will have the quantum computers will not tell you, right? Otherwise they have lost their edge. So it is likely that we will not know. So how do we protect ourselves against the threat of a quantum computer cracking our public key infrastructure? There are many ways to do that. One way, which has been demonstrated recently or sometime earlier this year, was China. And here is a nice picture that shows what they actually demonstrated. They have a terrestrial link of quantum key distribution going from Shanghai in the south to Beijing in the north. Along the way, they go through the cities of Hefei and Jinan. And at each of these locations, Hefei and Jinan, they have smaller networks that distribute these secret keys to different users within the city. China also has demonstrated satellite-based quantum key distribution. So these are all motivations for us to say that these are ideas that we can translate, we can take them out of our labs and into the field. What is it that we wish to do in India? We have the National Knowledge Network, and this National Knowledge Network connects a lot of the universities, a lot of the government infrastructure. And the idea is to secure this against potential eavesdroppers. And this is enabled using quantum communications. The backbone data rates can be as high as 100 gigabits per second. And that is aggregated traffic, but not all of it needs to be secure. So the most critical infrastructure you can secure through quantum communications. As a start, under the Center of Excellence, what we have done is we have proposed the Metro Area Quantum Access Network, or MACAN. It's a nice catchy acronym. So MACAN is our first attempt to take it into the field. We are connecting IIT Madras with the IIT Madras Research Park through the Society for Electronic Transaction Security down to NIC. The NIC building, for those of you who are familiar with Chennai, is near the beach at Besant Nagar. And through the NIC center, you actually get access to the national backbone. So the first field trials that we are hoping to be able to do sometime next year, pandemic allowing us to do it, would connect IIT Madras to NIC through the Society for Electronic Transaction Security. The distances are not very long, but one expects that we will have enough challenges in implementing something like this. What are the types of challenges? One of my colleagues actually has been working on qubit queues. There's a very nice, catchy rhyme that came up after they posted their paper. How to queue a qubit if a qubit will not queue. So these are photons, they don't like to wait around. And so if you take classical information and send them down our quantum channels, they get lost. And when they reach a network node, they're not waiting for any more photons. They just need to keep moving on. And which means that if you send a stream of bits, instead of getting 0, 1, 1, 0, 0, 1, you get 0, 1, you lose 2 photons, you get another 0, you lose a photon. You lose another photon. So there is a dead time in every detector, and the classical ways of thinking about queuing theory does not work very well with quantum optics. So they have developed the theory for quantum queues or qubit queues in a photonic erasure channel. all these colleagues will be there in our panel, and I do hope that you will have questions that you can direct towards them. So the next big target that we have after we get to the National Information Center near the beach is to go all the way to Delhi, right? And how are we going to do it from Chennai to Delhi is by routing it via Bangalore, Hyderabad, Bhopal, and then reaching Delhi. And at each of these cities, we will have our own metro area quantum access networks. So this would become our national quantum secure network. This would be the first attempt that we have of going up to 2,500 kilometers using the idea of secure nodes. Quantum key distribution and quantum communications itself does not work beyond 100 kilometers for various reasons that are familiar to those who work in fiber optics. But it is possible to build secure nodes and build such a terrestrial link. And this is going to be our goal for the next phase of our center. Coming back to the basics, what are we actually talking about is a quantum key distribution system. And I put this picture up to tell you that not everything is quantum. The word quantum channel and quantum is actually about 10% of the work. There's a lot of work that is done in the classical channel by people familiar with information theory, embedded systems, electronics, fiber optics, that convert these quantum keys into secret keys that are then fed into encryptors, and then they encrypt your communication, which is running at potentially at 100 gigabits per second. The key exchange rates are themselves fairly low. They're only at 100 kilobits per second. And so one has to be careful about using them to encrypt large amounts of data. The other things that we can do is rely on the properties of light. We rely on polarization, we rely on dispersion, we rely on phase for a lot of our demonstrations. What we have done is build quantum random number generators. That's also fairly easy to do. If you take a single photon and hit it on a beam splitter, they will go to either one of the two detectors following a reflection or a transmission, and that can be truly random. Similarly, the spatial mode of a single photon when it hits a CMOS camera can be random. The time of arrival of a photon can be random. And you can combine all these ideas to build quantum random number generators. And we have done experiments like this. They're fairly easy to set up. And if there are students in the audience, I would encourage you to actually think about setting up experiments like this. And they pass all the test suites for randomness, which is not a guarantee of a quantum random number generator. There are certain tests that you have to run to ensure that these things are truly random. What gives us the ability to think we can take it from Chennai to Delhi? Well, we have done our own demonstrations. We have gone up to 100 kilometers using a form of quantum key distribution called differential phase shift QKD, where a single photon is in a superposition of 3 states or 3 paths. And these 3 paths then can be modulated using a phase modulator and then detected using a delay line interferometer. On a classical oscilloscope, you'll see 4 patterns. If it was a single photon, you would see the photon clicking either in time slot D, C, B, or A. And you can infer a key from whether it clicks in time slot B or time slot C. This kind of behavior is also easy to do, but it takes a lot of engineering to precisely stabilize the system and keep it running for many days. You can also do computing with photons, and this is an idea that I'm hoping my colleague Bijoy, who works in silicon photonics, will be demonstrating. We have computing with photons using polarization, and this was postulated by Jeremy O'Brien in 2007, and his company PsiQuantum has now raised $450 million to build a quantum computer with at least 1 million physical qubits. So there's a lot of stuff that you can do with photons. The technology platforms at our center, which are revolving around this idea of photonics, also includes silicon photonics, as I just mentioned, diamond photonics. Diamond is another platform that is very useful because it works at room temperature. That is one of the joys of working with optics and photonics, is that a lot of the work we do can be done at room temperature. Out here, qubits on the cloud is a picture of a quantum computer that actually works at 4 Kelvin. So people are interested in looking at platforms that can work at room temperature, and we do a lot of the work on quantum sources, quantum random number generators on these platforms. Whereas the work that we do on machine learning, quantum algorithms, we use the machines that are available to us on the cloud. There are certain ideas that people have explored with diamond photonics using quantum repeaters. So if you really do want to go from Chennai to Delhi without what we call secure nodes, you want quantum repeaters. These are the equivalent of an optical amplifier. They're still early days for this, and my colleague Praveen should be talking about that later this week. We have also worked on masers. These are the equivalent of lasers, and they are a coherent source. So if you're looking for a very good source of microwaves at gigahertz, about 2.8 gigahertz, then these masers become very useful for that. It is a curiosity that masers were actually discovered before the lasers, and although the lasers became very popular, the masers did not until the advent of diamond photonics. So there's a lot more to talk about. I've used up most of my time, but I will just very briefly introduce to you a few other topics. So there's quantum tomography that my colleague Professor Lakshmi Bala works on, Professor Prabha Mandyam and Professor Pradeep work on a lot of the information theory, quantum error correction, topological quantum codes. And as I mentioned, Praveen works on nitrogen vacancies in diamonds for quantum repeaters and masers. So in summary, we have a Q team that goes across a lot of the departments. I've added Chaitanya here from the chemistry department because he's promised to help us with doing a lot of the simulations of the chemistry molecules. And we have faculty on our panel today from all these departments: electrical engineering, Department of Management Studies, mechanical engineering, and physics. I am also thankful for a lot of the financial support that we have received over the years from the different agencies of the government and IIT Madras. Thank you very much. So I could probably take some questions from the audience, or we could go directly into the chat, into the panel discussion.
There are already many questions in the Q&A, but I haven't seen, none of them say, Anil, please tell me this, at least not that I've seen. They seem to be more general questions as I read them.
Okay. Well, one of them I think says, how does quantum computing use for defense applications? Well, maybe we can start by letting some of our panelists introduce themselves, and then maybe we can then go down to questions. So there is someone asking about qubit noise, for example. Prabha, would you like to take that?
Yeah, sure. Thanks, Anil, and thanks, David, for agreeing to moderate this session. Fact of the matter is, David is probably best placed to answer the question on qubit noise. But I will say a couple of sentences maybe, and then actually we could have David answer some of the questions as well. Quantum states, when we prepare them and we would like to use them for computing and so on, do not exist in isolation, right? They always, they're not what we call technically a closed quantum system. They are open quantum systems. They do interact with the environment, and this interaction is not something that the experimenter can often control. And quantum noise or qubit noise is a result of this uncontrollable but also unwanted interaction with the environment. And part of what I do, which is quantum error correction, is to try and mitigate the effects of this noise or this unwanted interaction with the environment.
Yeah, maybe I could mention, but of course, I'm now going to be moderating the next little section. I will not just do any monologues. I want to invite all of your colleagues to pitch in. I thought I would tell one little story, though, because one of the questioners in the Q&A said, what does this have to do with defense? And I think you already covered this, Anil, in your talk, but to give a personal experience, in 1994, when Shor's algorithm was announced, we heard, I was working at IBM at the time, that there was a great panic in the national security community of the United States. And they called a conference rather quickly because from what they read and what they were hearing about the possibilities for quantum information processing, they saw that this was going to completely annihilate their assumptions for security and require them to immediately, base security on entirely different principles. We had that conference and we had discussions with those people who were very smart, but not all of them with physics background. But when they started to learn about quantum noise and quantum decoherence, they got much more relaxed. They said, oh, I see. This is a beautiful idea and maybe, but it will be a rather slow evolution towards a revolution. And I think that's indeed what we see, that we're sort of, quote, halfway there to the point where it does profoundly affect what can be computed and what cannot be computed and what can be done securely and what cannot be done securely. So, and you should take halfway in a very, very loose sense, sort of by orders of magnitude. We're now 30 years from these, or 25 years from the first discoveries, and think 25 or so years until the entire world is changed. Okay, now, Prabha, I know that you have an amazing collection of colleagues here, many of whom I have not met since I've only been on your campus one time, slightly before Corona. So how should we proceed? I loved one question of, what does this have to do with engineering? And if I'm a systems engineer, do I have anything to do with quantum computing? And so I will maybe take the chance to look around, but you can help me. Do we have someone among your experts who could really try out the answer to that question?
Yeah, we do have 3 or 4 colleagues from the electrical engineering department. So there's Professor Bijoy, there's Professor Deepa. I don't think Professor Nitin is here. He's probably the best placed to take the question on systems engineering. But I don't know if, and then on the theory side, we have Pradeep and Krishna, who are theoretical engineers, if I will, or more mathematical engineers. And then there is Deepa and Bijoy. So maybe if one of them would like to take the question.
Yeah, electrical engineering is a tremendously broad discipline. So it represents many different points of view, and not all electrical engineers are systems engineers. But but can someone speak up? I'd love to see some.
Deepa would, or Bijoy can. Yeah, Bijoy.
Please go ahead.
Bijoy, you're muted.
You're muted though.
Sorry. Yeah, thank you very much for particularly David and Prabha, Anil, nice presentation. And also the question is also very relevant to me, I thought. So, all this QKD, quantum key distribution for secure communication and also computations. So different technologies being evolved. One of the technology I can give you example that so on-chip quantum computation, on-chip QKD, etc. So on-chip means something you can control qubit on-chip. And for that, you need a lot of classical devices, waveguide devices, sources, detectors, etc. And then you need, as an engineer, what you can do, how to make them compact, efficient, energy efficient, and so on, so that you can have a scalable system. So in that point of view, not only needed some design engineers, also device engineers, as well as packaging engineers, and ultimately the packaged chip, how you can use in a system level applications. That type of solutions one can expect from any sort of engineering students. So that could be my take. Yeah.
Yeah, I agree with that point of view from what I see, in other parts of the world, that the quantum physicists have done a great job, producing phenomena, but to actually turn those phenomena into working devices, into working, systems, requires a whole different mindset and many different capabilities. But starting from what we know today, but really stretched into other realms, like how do you do all the things that you just discussed at 4 degrees Kelvin, or even lower temperatures. So thanks. I'm now going to turn. Now I'm really scared by our Q&A, which has 83 entries and growing. So how we find a good sort of selection of things to do in these
David,
few
can I
minutes.
suggest this one? I just saw this one. It says, why isn't there a standard optimized lattice topology which works best? Does it depend on the gates that are implemented by the processor?
Yeah, good.
Not entirely sure whether there's anyone more qualified than you to answer that.
Well, I don't know. Of course, as you've shown in your talk, quantum information and quantum computing is very broad, and not everybody can cover everything. And I think these are one of the areas of expertise that's not really centered at Madras, but which is highly relevant, in the Google company or at the Chinese Academy of Sciences, or various, organizations have very much run across this. I think that's a not complete discussion yet. I mean, and it's involves an interaction between what's practically doable and what's desired by the architects, the computing architects. I think that the reality of the matter is that we can only have local interactions on chips with solid state components. That's the one I'm most familiar with, and we can understand that that is acceptable. That there are architectures for running quantum algorithms that can effectively use networks of locally connected qubits. But it is some hindrance. And of course, in optical quantum computing, it's possible to have longer distance links. But I think it's still really a matter of basic research of seeing, how much which architectures will really end up with as the best ones for quantum information processing. There's also the issue of whether you'd like your processing to be distributed or not. And that's where the fact that you can do quantum communication makes that a conceivable objective. And we have many great ideas, which will take, we're still only halfway there, so to speak, to being able to really test them in the laboratory. So yes, I agree. That's a good question. I'm now turning my attention again to the Q&A. But does someone someone here want to pick up any of them and either discuss them or throw them back to me?
There's a question on whether there are any limitations on quantum channels and how they are different from classical channels. I think the question is about comparing the performance versus limitations of quantum versus classical channels. Maybe David, you could take that.
Okay, although of course you're equally capable in that area, but I mean, we know, not surprisingly, the quantum channels are more delicate or more sensitive to noise overall than digital communications channels, because you cannot easily simply use the strength of the signal as something to combat noise. So you have to be more clever, but there are quite powerful coding methods that have been worked through, and which do give the prospect of using quantum channels highly effectively. But it has to be understood that they only come into play when you can really deal with the channel one photon at a time. You really have to be able to control your radiation at the quantum level before these techniques come to be useful. But if you if you lose 30% of your photons, that's still okay. But if you lose 50% of your amplitude of a signal which contains 100,000 photons, you're not okay, generally speaking. I can say that this is a theme that I'm very interested in the sense that, photonics is of course a real and well-developed science, and it's about, the quantum nature of light. But in the work that I'm involved with, and many solid-state qubits require use of microwave frequencies, or even RF frequencies. And in past times, I remember when people thought it was absurd to even talk about photons for radio frequency radiation. I mean, we know theoretically that, one should have such a description, but I remember a very eminent quantum optics professor at Caltech who said, as far as I'm concerned, photons below 100 gigahertz don't exist. But now we know they do exist, and actually the impetus of trying to do quantum computing has made it necessary to manipulate even microwave radiation at the single photon level, and now one's capable of doing it. There are now ways of creating, a source for single photons, microwave photons, a way of detecting at the single photon level microwaves. So this is an entirely new development in quantum science, and it seems like it will have big implications for solid-state quantum computers. Okay, so that's one line of thought. I see the number of Q&As has only grown while I've been speaking. So again, I need help to even consider what to address in the few minutes that we have. I see, well, of course, I see some questions that maybe shouldn't be, for general discussion, but I love the question about, does this have anything to do with LIGO India? As it's an area of physics I love, actually, gravity wave detectors. The answer is yes and no, actually, that gravity waves themselves are, how should we say, not very quantum. Although even that is not in principle true, that there are such things called gravitons, and we believe as a matter of principle that gravity waves are streams of gravitons, but it is really inconceivable to detect one single graviton, but you have a gigantic mass of gravitons flying past, and then you have some chance of detecting them with LIGO. And with LIGO India, we'll have a better chance of detecting such, tidal waves of gravitational radiation. Now, but quantum techniques are actually in use in the detector because gravity wave detectors act by moving masses by tiny amounts, and the detection of the motion of those masses is done with optics. And techniques of quantum optics have been used and are in use actually in some of the LIGO stations to enhance the performance of the detection of the motion of mirrors. I actually don't know whether LIGO India will employ these so-called squeezed light techniques. And I see the answer is yes. But I bet this is off topic because, India is a big place, and I bet the experts are not the ones at Madras who are working on this. But I'll look for my colleagues to answer that one way or the other.
Very much. They're very much at Madras also.
Well, excuse me. Okay.
Deepa out here is on the panel. She works on 2-micron lasers for advanced LIGO or the next generation. And we are also building a squeezer in our labs for many reasons. The squeezed light is also used for computation. So one could look at doing quantum computation with squeezed light. And so that is one of the projects that we do undertake at the center. And it has its applications in LIGO.
Okay, I stand corrected. Thank you very much. Of course, the quantum science, or the area of quantum science, is broader than the whole area of quantum information and communication, but they interact strongly. So people who do gravity wave detectors will not be, inventing the next quantum computer, but they'll be using our general growth of knowledge of quantum techniques to well, to change the world, in that case, to change the world of, well, our knowledge of astrophysics. Well, this I find a challenging one. I'm sorry, I'm doing this a little bit at random. I mean, this one I find a challenge to relate. Can chemical engineering relate to quantum communication? That's a real span of disciplines, I must say. I think that means that among the audience, there are some chemical engineers. Welcome to you. We don't know, well, to me, all chemistry eventually becomes chemical engineering. And so all new knowledge of chemistry eventually becomes used in engineering. Actually, one of the techniques or one of the problems that has seriously been analyzed as a problem in quantum algorithm theory is to understand the exact metallo-organic interactions that are responsible for nitrogen conversion in bacteria, I suppose, but which are responsible for the creation of you know, a large fraction of the biological nitrogen that exists in the world that is produced in nature. And that's a very complex center. You know, that molecule has a whole cluster of metal atoms, and it's surrounded by a gigantic organic complex. And there is a serious question, could quantum simulation be a tool for actually understanding the mechanisms of that center, which are currently not really understood in detail. Now, the question, the anonymous attendee asked whether we could relate this not to quantum computing, but quantum communications. That's an even harder connection, I have to say, because we don't at first glance think of using quantum communication to run simulation algorithms like chemistry, but why not? In fact, that is any instrument like the one that was mentioned in the talk that uses photonics to do quantum information processing is, in a sense, at the same time, a communications apparatus and also a computing apparatus. So there I've managed it. I've even connected quantum, I've connected quantum communication with chemical engineering. I bet, though, that you don't have any chemical engineers in the center. True? I'm looking at a few of you who are visible here.
I think we do have someone who from the chemistry department who works on or is it looking into variational quantum eigensolvers and such, yeah. Which are today being implemented on these NISQ devices. Okay. So I think we do have some interest on that.
Yeah, but I was being a little bit specific there that, you know, there is actually chemical engineering, and that's, well, I believe at IIT, a different department, right, than chemistry. That's
indeed, usually... indeed, yeah, yeah. As far as I know, we don't have anyone from chemical engineering.
Anyone else of the faculty who has been scanning the now 112 open questions to see if there's one that they would find interesting to address?
So David, there are a couple of questions about architectures in the sense, what are the different ways to realize qubits, and a specific question on silicon qubits, which maybe I thought you could address.
Okay, well, back to me. I think that you do have silicon experts, but there's, you know, silicon is many different things, and there's silicon photonics. But the area that I'm quite interested in and involved with, and my colleagues at RWTH in Aachen work on very actively, are silicon quantum dots. So, you know, something that we've arrived at as the result of many decades of research in nanotechnology and nanoscience, that you can make nanometer scale quantum dots of silicon of just the right sort, so that they can host individual electrons. You can, with the right tuning of gates, you can drop an electron, you know, one single electron into such a quantum dot, and into such one each into an array of such quantum dots. And then the spin of that electron is a natural two-level quantum system. We say spin up, spin down are the only permitted quantum states of the spin of the electron, and that's so therefore also encodes a qubit. And then you have to think through all the many different schemes or all the many different steps that you have to take to turn that into quantum computing. And we are part of the way down that road. Nearby dots can be entangled by, again, just by suitable manipulation of quantum gates, of classical gates, of voltages. Carrying entanglement over long distances in such structures is still a bit of hard work. So that's actually the research that's done in our labs here to, right up to the minute. So silicon is a contender. It definitely has not checked all the boxes that superconducting devices have checked, so that the most advanced processors currently and the ones that people push ahead to make large devices like the ones that you saw in Anil's talk are not made of silicon, except all the supporting infrastructure, all the FPGAs, all the generators, all the detectors have silicon all over the place in them. But silicon as a quantum material, well, that's mainly what I've just summarized there.
Thanks, David. So there was a question about entangling photons and the use of photons in quantum computing and so on. We have Professor Lakshmi Bala here, who's an expert on quantum optics. So I know she's been answering some questions in the chat, but maybe she wants to talk about a couple of these questions.
Well, actually, I thank you, Prabha, and thank you, Anil and David. I did answer some of those questions in the chat box, similar questions. The simplest way of entangling photons is by just passing them through a beam splitter. The beam splitter comes with 2 input ports, and even if the photons are unentangled, at the output port, you will find that they are entangled. In fact, you could make some analogs of Bell states by passing photons into the beam splitter. That would be a very simple way of doing it. There are many other ways of doing it too. You could have atoms interacting with photons, and in fact, there are very interesting aspects of such hybrid quantum systems, as we call it, that you see in the laboratory. You see entanglement, sudden death, entanglement, sudden birth, and so on. You could entangle objects that way through the atom as a mediator. So several such platforms are available for entangling photons. I think that should more or less do as a first level answer.
There is a question here that might be interesting also. It says, could you please comment on neutral atom quantum computing apart from trapped ions and photonics?
I think Anil is a better person to comment on.
Not really, but not really. I do know that cold quanta has been in the news of late because they have been able to, I believe, go up to 100 qubits or 16 qubits. I don't remember what the number is. But that's fairly recent. I mean, within the last year, I think, is where they've been making the news. David, do you have any sense on where neutral atom computing would work vis-a-vis trapped ion?
I know something about that, but that's sort of on the opposite side of Germany. Germany's not such a big place, but if you look over in Munich, you find the world experts in these things. But at least for me, that's far away. The principles of that were already articulated 20 years ago or so, and they indeed involve traps. So you should use your lasers to trap neutral atoms in various stable structures. And then again, use mostly light to control the evolution of the quantum states of those neutral atoms. And I think beyond that summary, there's a great variety of possible detailed approaches, which I'm not so familiar with. Some of them involve using Rydberg states, very highly excited states of atoms. I know the application areas that community has focused on are mostly simulation problems. So simulating other many particle quantum systems and solving problems in many body physics, which of course is not so distinguishable from the problems of, say, quantum chemistry or of materials science for quantum materials. So yeah, that's about all I would say about that.
I see a question
to
here
thank-
for
I want
all
to
the
thank
physicists.
many-
There is,
sorry, I want
is
to
there
thank
any
the many-
scope in future in quantum physics?
Sorry, say that again.
Is there any scope in the future for quantum physics?
Scope in the future.
I
I
mean-
feel quantum physics will be with us forever now, I think. I think it,
I guess from a student's perspective, a lot of the questions are about, what is a good path? How do engineers get into quantum physics or quantum engineering? Should students of physics pick up something like this as a specialization? I think the question is more broad-based in the sense of the uncertainty of their choosing a career path. Right? And I think perhaps, Arul, do you want to take that and sort of say something as the head of the physics department? Perhaps you could address something specific like that.
I didn't know that was a job of the head of the physics department. So what exactly is the question? What is the scope of quantum physics? Well, as David said, quantum physics is here to stay. It's the science which is underlying the technology of systems which are microscopic, especially, but technologies which are going to be deliberately using quantum mechanics is on the rise, and that's what, in fact, these series of webinars are about. So in terms of scope, I would say that, yes, it's a good scope for physicists to go into. It's as simple as that, yeah.
And in a similar sense, I'm seeing a lot of questions. How does a mechanical engineer contribute? Is there a contribution
well, since Anil brought me into the equation, I'm a mechanical engineer, so
okay.
if that helps. No, I mean, in all seriousness, even there are oscillators at the, nano scale oscillators. So I think we should not think too much in terms of boundaries of subjects. After all, quantum mechanics is mechanics also. So, right. So, well,
yeah, I'd like
everybody is welcome to the party.
I'd like to, in a sense, endorse that point of view.
Yes,
that this is now a statement to persons who are studying at universities that you cannot expect, it's not like being trained to be an accountant. There's definitely more uncertainty in studying in a university than studying for other kinds of careers, because it's not intrinsically a study for a specific career. It's an acquisition of advanced understanding that then, if you have successfully acquired that advanced knowledge, you can apply it in many, many different ways. When I studied at university, my research project was principally about a quantum material which has completely disappeared from any interest, which never had any successful applications, and which was not, didn't turn out to be a career for anything. But I immediately moved into other subjects and went through many, many changes of subject. And well, have been staying for a while in the subject of quantum computers, but maybe there will be a next subject and a one after that as well.
Okay, we have almost hit the hour, so
yeah,
I don't think we'll manage to catch up with all the questions. I think they come faster than we can answer.
Yeah, but thanks for all the people, your colleagues, who have been busily, quietly answering many of them. So I see many answered as well. And indeed, I can't, and I don't think anybody can answer all the questions that have been posed here. So should we indeed wrap it up? And of course, I wish you a great success and luck in the further work of the center.
Thank you very much, David. And yeah, I think Richu is here. So maybe, Richu, any closing remarks? Oh,
thank you, Professor. Yeah. Thank you, Professor Anil. Thank you for the talk on quantum information, computing, and communications. I must say this, amidst all the 44 webinars we've hosted so far, this is where we've really seen a quantum of questions, which is ever growing at a steady state of speed. So thank you, Professor DeVincenzo, for answering all the questions. And we also thank all the panelists, distinguished panelists, for answering these questions coming from a wide variety of disciplines. We've had a very good participation. We've hit close to 700 participants for today's session. And our Q&A box is still growing. So we'll collate all these questions and we can send it to Professor Anil for your reference later.
Yeah, please do that. Thanks.
So a note to participants, please stay tuned for more webinars under this cluster. We have 2 more webinars coming up on the 16th of September under Quantum Science and Technology cluster. Thank you, participants, and thank you, everyone. Good night.
Good night. Thank you, David.
Okay. Okay, bye.
Thank you,
Thank
David.
you. Bye. Bye. Thanks.
Bye.